Okay, hi, good afternoon, everybody. My name is Connor Bush, and this is my homework 3 submission for process dynamics and controls. We're going to be revisiting what we had with homework 2, part C. We had an exothermic CSTR reactor. However, in this case, we kind of want to start looking into what plug flow reactors look like. So we are going to divide the CSTR into 15 CSTRs in series, almost a discretization of that to model that plug flow reactor environment. So now we have to divide the volume and heat transfer parameters by that number of CSTRs in series, 15 in this case. Volume because it's a sort of that dimension in space, we are dividing that physically. And then also this heat transfer, the coefficient multiplied by the area. This area is also being discretized into 15 segments. And then we are assuming that at time is equal to 0, that all 15 CSTRs in series are at 350 Kelvin with 0.45 molar concentration of A. The inlet feed temperature is 350 Kelvin, and that the concentration of the inlet feed is 1 molar concentration of A. The coolant we're using, because it's an exothermic reaction, we need cooling. The coolant in the jacket is at a constant 290 Kelvin, and then all of the other parameters from homework 2 part C apply. We're going to derive the time-dependent material energy balance equations, and then we're going to simulate the concentrations of A and the temperature of each of the CSTRs as they evolve over time. So I'm going to pull up, this is the code that we had from homework 2C. So we're going to just modify what we have here. All of the libraries here we're going to be using, and then let's look at what the parameters we're working with. So this flow is going to remain the same. The concentration in, it was said that that's going to remain the same with the temperature of the feed. This volume here, this is where we're going to have to start the modifications. We're going to need to introduce a new parameter. I call that N. This is the number of CSTRs in series. This is where we divide by that number. We're going to leave that as a variable so we can change it if we would ever want to. I'm going to assume density is the same or constant throughout. The heat capacity is the same. The heat of reaction will be the same. And then this activation energy over the gas constant will remain the same when we use that for the Arrhenius equation for our K values. This initial K value is going to remain the same. And then this heat transfer coefficient multiplied by the area, we're going to divide that by N as well, as stated in the directions, but also because we are dividing that area into 15 segments. This is the coolant temperature. And then since we are going to have 15 CSTRs, we're going to have 15 separate initial guesses for concentrations and temperatures. So we're going to need an array. And the easiest way to do that is to use this numpy.full. So here it says what shape we're going to have that N, and then the fill value is going to be the concentration that we want to use. Then similarly here, we're going to make an array of nth length. This is just a 1 row vector, and then we have our initial guesses for our solid IVP once we get to there. So we're going to leave t end, same with 10 minutes for now. We can always go back and change that. So here we have two sort of parameters for the differential equations we're going to be looking at for this function. The time we're going to leave alone, but this vector we unpacked with the concentrations and temperatures. However, these are going to be arrays now, not like individual numbers. So we're going to split this up. So this CA is going to be, so this vector we're going to be looking at, we're going to eventually concatenate these two. So it's a 1 row vector of all 15 of the initial concentration guesses and then all 15 of the initial temperature guesses. So to model that here, for the vector, we're going to start at the beginning value, starting from 0. We're going to go to N. And then since we're stopping at N, it does not include N. So that means that our temperature, we're going to start at N and then go to the very end here. So this vector V is including all of our concentrations and all of our temperatures in a one row array. This K, we're gonna have 15 individual K values, like one for every single CSTR in series. But we can leave this alone for now. We're just gonna have to call or use indexing. Once we modify these equations here, we're going to have two separate forms of equations. We're going to have the dCA dt for the first CSTR, and then for the remaining CSTRs. So we're going to use these equations here that we derived last time. Excuse me. And I'm going to call these dCA dt not dt dt not, as this will be the first value in this vector here. So our CAN we're given, that remains the same. This Q is untouched. However, here is when we need to start using the index. So we're going to start or use this initial, since we're just looking at the very first CSTR, we're calling the very first value in the array. So we start at 0 for indexing purposes. We've already adjusted volume up here in these parameters here. And then this K, like I was saying, there's 15 separate K values. So we're going to need to call that 0th K value. And then again, these match here for the very first number in the array for the concentrations. Similarly, this Q is untouched, this flow rate is untouched, this temperature in we're given, and then this difference here is represented by the difference between what is coming in and that very first value within that array of temperatures. This volume here, again, untouched. Same with this heat transfer coefficient multiplied by the area. Heat capacity is constant, density is constant, V we've dealt with. And then here, this difference between temperature, the cooling temperature, and the temperature of the reactor, that is our 0th index temperature to be consistent here for the first CSTR. Negative heat of reaction, that's constant. And then the very first 0th concentration, same with the K value, constant, constant. So we should be good with our very first CSTR for the differential for the concentration and temperature with respect to time. And then looking at the remaining CSTRs, we're going to have to modify this a little bit. So we're going to want to start from the very first. So this includes the 0th one, but we want to go to the end at like the very end one, but not including that. Because if we look at the difference here, we want to have like that overlap where we're subtracting the initial from what's leaving. So if we start, since we have this 0th index already, we're starting at the one that's following. So 1, and then going to the very end there. And then this is the sort of notation that we're going to use for this K value, this CA value, and then following similarly into the temperatures. So this volume untouched, K value, we want to call the first one to the very end of all the values, because we've already used the 0, 1 to take into account the first CSTR. And then same thing here again. So now into the temperatures, we're going to use similar notation when we're looking at the difference in temperature. We're going to include beginning value up until n-1 essentially, and then going to start at 1 and then go to the very end here for the temperature. This is essentially like the inlet minus the outlet, where the outlet is the following inlet temperature for the next CSTR in series. These are untouched, these are constant, that's untouched, already dealt with. And then we're looking at the first to the end. For that, a little repetitive, but making sure everything matches. These are constants. Now, we're going to need to combine this initial concentration with the remaining, and then similar with the temperatures. So to do that, we can use this numpy.r underscore sort of formatting where we're concatenating these two arrays regardless of the like shape of them essentially. So if we say this dca dt not dca dt, we're adding this value into this array. You could say basically, so we're starting here and then all the remaining values are going to be those afterwards. And then same thing for the temperatures. And then after this, we're going to need to concatenate both of these. This is essentially saying we're putting it into a one row array. So we can concatenate both of these. So it's a single one row array, starting with all of these values of concentration and then all of these values of the temperatures. And then what we need to do, instead of saying np.array, we're going to concatenate these from here, making sure everything's good, because we can combine these since they are both one row, the shape matches, so we can concatenate. And then when we're going to plot now, we're going from 0 to 10 minutes with 500 time points in between, evenly spaced. I'm just going to call this CA T. And then we're going to need to reshape this vector. So we're going to want 2 rows of n columns, and then we'll match the 500 time points here. So I'm just going to delete this and then call this fig CA for the concentration plot. We're going to need to do a for loop. So for I index in range n, so for all in range. For all 15 CSTRs, we're gonna add scatter. So we're adding a point for each of these. So our X value is gonna be this time plot of the 500 evenly spaced values from 0 to 10 minutes, whatever we have set. And then our Y is gonna be, we're gonna call this array, each index I for all values. So I'm going to leave that as a colon. It's going to be row 1, column 1, and then we can name each point CA. And then if we use these brackets and this F, this is the sort of syntax we can use. So for each point, it's updating and renaming for each iteration, starting from 0. And then we're going to update the layout. So we're going to say height, we'll call it 500, a width of 800. And then, like Carlos, I enjoy the dark sort of template. So as you can see, 10 is kind of an overshoot, 10 minutes. So if we zoom in here, we can see around 1 minute, we get a better view of things. So if we go back and update all of that, this kind of gives us a better look. So this is representing the concentration of A and each of the CSTRs. On top here, we have the very first one, then the second one, then the third, fourth, and then this kind of represents how the feed inlet is inserting all of the concentration of A at the maximum. That makes sense. And then it's sort of dissipating, it's disappearing, it's reacting. So as you can see, as it moves through all of the CSTRs, it's reaching that full conversion or full disappearance of A. So we're left by the very end of 1 minute. That's essentially the end of the reaction. when A is no longer inside of the CSTRs. So yeah, that's kind of a representation of this graph here. And then if we copy this over here for something similar for the temperature, I'm going to call it fig T. Update the Y values to use the array for T, update the name, layout, that should be okay. Okay, so, here. Might have messed that up because I didn't. Okay, that's fine. So starting from time is 0, we have this initial temperature, it's constant, steady state. However, once the reaction's beginning, that's when temperature is increasing. However, it's not a runaway reaction because we have the effective cooling. And then the initial CSTR is at the greatest temperature. However, it dissipates as it goes on. Makes sense. As cooling proceeds. And then as you can see around, for most of them, they reach all steady state around, I would say towards the end of these ones, around 1 minute is when steady state is reached for the temperatures. That makes sense because the reaction essentially is over. There's no more A reacting. It's complete. There's full conversion reached. So since there's no reaction, then there's no more heat of reaction being left over. So that's when we do reach this steady state because there's no change in concentration of A. So this is kind of a representation of what a discretized CSTR in series looks like. It's to mimic a plug flow reactor for an exothermic reaction when we apply cooling. So yeah, that's kind of everything we have going on there. Thank you.